Okay, then to regression. Now the aim of regression is to predict a response, or I'm underlining this because it's a technical term, or some people call this the dependent variable. From known regressors. I'm giving you a couple of alternatives here because different fields have given different names to these, or predictors, or explanatory variables, or features, or independent variables. So you see this goes together, the dependent and the independent variables. Well, but this is all what we've done in classification all along. Yes, you're right. But in regression, this response or the dependent variable is typically continuous. There are special cases where it is not, and one still talks about regression. But by and large, the big difference to classification is that in regression, we look at continuous variables, and in classification, we look at categorical outcomes. Now, this has many applications, obviously, to make predictions, or to interpolate. People in the business world would talk about prediction. Statisticians would be more modest and talk about estimation here. Sometimes the parameters themselves, the regression parameters, are of more interest than the actual prediction. In particular, how uncertain these estimates are. And sometimes you want to get a better understanding of your data by determining the most influential variables. That's related to what I've just said about the random forest variable importance. Okay, now the mainstay of regression theory is about linear regression. You've known this since high school, but let's see if you will see something new today. So first of all, it's important to note that linear regression it's linear in the parameters, not necessarily in the independent variables. I'm saying this because there's sometimes confusion here. So even something like quadratic or cubic regression would still count as linear regression, as opposed to nonlinear regression, where you really have a nonlinear function of your parameters. Okay, so here I'm writing a cubic regression that would still qualify as a linear regression because the parameters here are only linear in this equation. So if I'm writing this in a bit more generality, I can say that my response y is beta 0 transpose x plus epsilon. I will have a hard time with notation today. So today I'm underlining the random variables. So I'm saying epsilon. Normally you would use capital letters for random variables, but I want to reserve these for matrices today. So I'm saying that y and epsilon are random variables. Beta 0 is the true but unknown set of parameters. Y is, of course, my response. And x are the explanatory variables. And importantly, they are assumed to be free of noise. That's a pretty strong assumption to make in, well, in practically every application that I've ever seen. Because when you have measured your explanatory variables, then there's typically some kind of measurement error involved. Or even if you use a model, I'll give an example of that later, you might have a slight misfit between your model and reality. But anyway, for regression, this is assumed to be known and to be known exactly. Okay, so let's enumerate the assumptions here. That was the first assumption, that the explanatory variables are assumed to be exact. Then the second assumption is that the linear model holds. So we assume that the expectation of this noise term here is 0. Let me give an example where that would not be true. So let's say that the true function that you are going to, the true functional relation that you're studying looks like this, where we have here x and y. And now we have noisy measurements. And each time that I get a new training set, I would obtain a new set of realizations here. But the linear regression that I would fit would always be, let's say, a straight line here. And in this case, the expectation of the noise would not be 0. So if I made a different plot here of so if for each realization of my noise, or for each training set, if I obtained a new fit, and if I looked now at the deviation between what I fit and what I observe, I would see some bias here. So the expectation of my noise would not be 0. And that would be a violation of the assumption that I'm making. So if I observe this kind of behavior, if I observed such correlated residuals, then I would know that my model is not yet a linear model. So here, for example, I should do a quadratic regression. So I could turn this into a linear regression model by including not just x, but also x squared, like in the last equation on the previous page. Okay, so the second assumption is that the expectation here of this noise is 0. And the third assumption that I'm making is that the variance of these things is constant. Statisticians call this property homoscedasticity. And I'm also assuming that my noise is independent between different realizations. Now, by the way, if we knew, for example, that what the noise would look like as a function of x, then I could use this. So I could then, for example, obtain or perform a weighted regression. But here I'm just talking about unweighted linear regression, and this is why I'm making all these assumptions here.
So is the noise is 0 if you have a shape like that, the expectation. You just take every prediction and calculate the noise from the test data, and when you sum it up, you get 0 in this banana example.
No, because this is for a specific value of x here. So the expectation that I'm computing here is always for a given value of x. So I could stress that by saying this is y of x, and this is epsilon of x. And this expectation here is with respect to the noise, but not with respect to x. Thanks for clarifying.
And if we want to choose a derived regression, let's say x squared might not equal 5x to the power of 3, we just try each power of x and then minimize the expectation.
So your question is how to detect deviations from the model.
Best choose the best fitting power of x.
Yeah. So there are. So if I make my model here more and more complex by, let's say, taking a cubic, quartic, by including fifth order and so on variables, I get an ever better fit. In the extreme case, I obtain an interpolation of each and every observation. So I get a polynomial fit, let's say, of an uneven order. So it goes to plus infinity here and to minus infinity on the other side. And in between, I have interpolated each and every sample. So what you have to trade off is how does your lack of fit decrease as you introduce additional degrees of freedom. And there are tests that let you argue, so by going, let's say, from linear to quadratic, my fit became better by that much, but I've also gained that many degrees of freedom. So overall, was it worth it or not? There are tests which give that kind of answer. So that would be the statistical, mid-20th century answer. I think today the answer is always cross-validation. Okay. Because cross-validation is insensitive to any modeling assumptions that you are making. So that's what I would use in real life. All right. So by the way, I have not included any constant term here because today we're again using homogeneous coordinates. So the intercept is absorbed in an extra parameter and dimension that we add to the data. So remember when we had some variable x tilde, we get homogeneous coordinates by building a new vector which has x tilde and then a constant 1 in an extra dimension. And this way I can integrate my intercept in this parameter vector beta here. Okay, now let me write the same thing in matrix notation. And I have arbitrarily chosen to use the following. So my matrix X holds my n observations with p features each. This is not the convention that you find in most textbooks, but I'm using this convention because it goes better with the single equation. In the single equation here, X was 1 by p, and beta transpose was p times 1. And Y was 1 times p here. And this is why I'm now using this format here for my matrix X. And then I'm having my matrix beta transpose. And I'm saying that up to the random noise, this gives me my matrix Y. And I'm a bit unhappy here with capital Y. I could perhaps have used a small Y transpose. But anyway, let's go with that. So Y is about the same as B transpose X. And this is 1 by P and P by N. Or I could make this an equality by adding here a matrix epsilon, which is just a row vector. Okay, now one view of linear regression is to say that what we have here, if we forget about the epsilon term, it looks like many equations for a plane. Well, let me just sketch it in 2 dimensions. So you see, if we have just a single measurement, that's not enough to fit the parameters. But if I have 2 parameters and 2 equations, this is just enough. And now as I get more measurements, I start to have an overdetermined system. And note that unfortunately, due to the noise, all of these straight lines or planes, they do not meet in exactly one point. So this is why we're somehow looking for the best compromise. And the best compromise can be found by minimizing the sum of squared errors. Which is sometimes abbreviated like that. And the sum of squared errors I can now differentiate with respect to beta. then I obtain this term of y transpose, which is independent of beta, so it does not appear. Then I have y x transpose beta. Actually, I have the term twice. And I have to take the transpose of that, which gives me minus twice xy transpose. Plus, and then there's the square term here of beta transpose x transpose beta, which when I differentiate it gives me twice and I'm looking for an extremum, so I'm setting this to 0. And this gives me the so-called normal equations. And solving these will give me my parameter estimate beta hat. So I can multiply from the left with x transpose to the minus 1. And this gives me my parameter estimate. I'm also putting around the box here because we will need this equation again and again. And I much prefer this matrix notation to the coefficient-wise representation, because in matrix notation here you can really, write it down cleanly in 2 or 3 lines what your regression parameters will look like. Now, I can insert this parameter estimate to obtain a prediction. My prediction y hat, I'm now inserting the parameters that I found. So beta hat transpose, I'm just taking from the line above. And that can be summarized as a single matrix. So y hat equals y times h, and this is why this is also called the hat matrix, because it puts the hat on y. Finally, a name that makes sense. Okay, and this hat matrix is a projection operator. So you can verify yourself that when you apply it twice, it's the same as if you had applied it once. It's idempotent, and it projects onto the row space of X. And it also allows us to express the residuals. Residuals are y minus y hat, the true dependent variables minus our prediction. The predictions we have seen can be conveniently written by using the hat matrix. Or I can rewrite it as y times the identity matrix minus the hat matrix. So these are the residuals, which are also of dimension 1 by n. Okay. So that was least squares regression in 3 lines. After the break, we will see how you can, in addition, obtain the covariance matrix for the parameter estimate. Any questions right now? Okay, let's have a 10-minute break. So, using this kind of formalism, one thing that you can easily derive is the posterior distribution of your parameters. So we are looking for the covariance matrix of our estimate beta, and I'm now in addition underlining it to say that yes, this is a random variable. The covariance is taken with respect to this noise term. Just as a reminder, what's the definition of covariance? So this is a vector, and we are multiplying it with its transpose. There you go. Okay, but now starting here from the first form, I am inserting the definition of beta hat, and we had found it by xx transpose to the -1 x times y transpose. And okay, I'm doing this explicitly. And now y itself can be rewritten as, or y transpose can be rewritten as x transpose beta plus epsilon transpose. And this is now beta 0, the true unknown beta. Now all of these terms here are independent of epsilon, and if I compute the covariance matrix or the covariance matrix of a shifted random variable, these are identical. So I can simply omit this first term here, and I'm left with the covariance of x transpose to the -1 x times epsilon transpose. And now in the first class of this semester, we had seen that this is a matrix, and if I want to pull it out of the covariance matrix, I have to pre and post multiply the remainder with it. So if I have the covariance of some matrix times some vector, it's the same as m times the covariance times m transposed. And I'm using this rule now. And this is now my matrix M here. So this is x transpose to the -1 x times the covariance of epsilon transpose. And now if you remember the assumptions we had made, then there was the assumption that this was independently distributed. So we have the identity matrix as covariance matrix with a spread of sigma squared. So this is sigma squared times the identity matrix, which I can omit. And then if you look at the remainder, once I've pulled this out in front, 2 of these terms cancel, and I'm left with sigma squared times x transpose to the -1. Okay, and from this result starts, well, several lines of work. For example, there's the entire area of optimum experimental design, which aims to give you the minimum possible uncertainty in your parameter estimates. So this was still without making any assumptions about the exact distribution of the noise, but if our noise was a normal distribution, if it was normally distributed, then this would give us here the covariance matrix of the posterior distribution, which would also be normally distributed. So I want to stare this equation for a bit more because it's so important. So note that in here appear only the independent variables. What it tells me, for example, is the following. If, let's say this is my first feature, and this is my second feature, and I'm not plotting the dependent variable, which is now orthogonal on this plane. So regardless of the actual values that I measure for the dependent variable, if I have much, so the way I've sketched it here, x1 and x2 are independent because you see no correlation structure here. So this matrix here will be a diagonal matrix, and it will have the inverse spread on its diagonal. So x1 has a large spread. Taking this to the inverse means we get out a small multiplier. So in other words, the covariance or the uncertainty in my parameter estimate for beta 1, so the parameter that's associated with this first feature, is going to be small, and the parameter estimate associated with the second feature is going to have a much larger uncertainty. And the reason is, let me try and produce a 3D plot of the situation. So I was only making a statement about where the measurements are. I did not even say if the values are larger or smaller than, I did not make any statement about the y's. Okay, I'm just making a statement about where my measurements lie in the x1, x2 plane. And if you now want to fit a plane to these points, you will find that the plane is well supported in the x1, x2 dimension, along the x1 dimension, but it would be poorly supported in the other dimension. So let's say that these points that I've plotted here are really already the observations. Then I could draw multiple planes here, like this plane, or like that plane. All of these planes seem to be somehow compatible with these points that I've scattered here. And these two planes, they agree in their slope in the x1 direction, which happens to be 0, but they don't agree at all in their slope in the x2 direction. And this intuition is encapsulated by this matrix here. So I'm trying to say it a third time just because it's so important. Now omitting, or okay, let me draw correlated values this time. So if I want to fit a plane here to these points, this slope of the plane is pretty well defined because I have some points that are far apart, but the slope in the other direction is ill-defined because I have a little spread here of points that could support my plane, especially considering that I have noise on all the dependent variables. Is that clear? Is the intuition clear? Okay.